Well, today we are going to start talking about smoothing and mapping, a very interesting topic. It's also called Graph Slam, although it's slightly different, right, in essence, but the idea is that now we'll be estimating full trajectories. Before that, a couple of things about groups. I think everyone has a group or should have a group by now, right? We did some arrangements, there were like some people, but everyone has a group, right? Okay, good. So now, next step is we are going to do an announcement, maybe later or tomorrow, and we will open like some slots. Here, if you want, you can join a discussion with us, with TAs and me, and your whole groups, and this can be like a pre-discussion on your proposal, right? So you were saying, I imagine that you are interested in working on something, right? So you start this discussion. It's a little informal, but it might be useful. This is optional, you can do it or not, but I think it can help, right? And then there's gonna be the official proposal, which is, well, an assignment for 2 weeks or something like that. There's still time, but I think it's good if we start talking, narrowing down exactly in which topics you want to work, and then, well, you can look for more papers, materials, that's gonna be up to you, right? But I think, well, this initial, let's say, yeah, initial discussion on the topic, I think can be beneficial for everyone. Okay, what else? We have problem set to soon to be delivered, right? You still have 1 day. Later we'll be around if you have questions, Marcel and me. Well, there's not really much to say. There's already 1 submission. And yeah, well, if you haven't finished, I guess, yes, you have this on your agendas. Please don't leave this for tomorrow evening. That can be a disaster. Okay. So let's do a quick summary of what we discussed last day, the data association. We start discussing Euclidean nearest neighbor, if you remember. So this is just Euclidean distance, and then what we were doing is if we have, like, let's say a 2-dimensional pose of our sensor, of our robot, right, at any time, and then we see an observation, right, that should correspond to a landmark. Right, so this is the way we were defining why this observation should correspond to the landmark, right? So the initial one was the closest distance. So, well, here, yes, exactly. This is not exactly landmark, because landmark, you know, this is x and y, while z is range and bearing in our model, right? But actually, what we need here for this is the observation model. Okay, so we discussed basically entirely the whole day about this, how to do the best association. Then, well, the next natural question was, okay, so this distance might not be significant, right? What happens when you actually have covariance? You have uncertainty on either on your position or your landmark, right? So then the term of what is closest, what is farthest, far away, it's not as simple as with Euclidean distance, so we need to weight things according to their covariances, right? And this is Mahalanobis distance. The same algorithm, you just go evaluate all distances against all observations, and then with this you get this greedy approach. It gives you a correspondence, but, well, we know what happens, that we might be assigning correspondences to the same landmark, right? And that was like something that it was not that good. Okay, later on, we derived the maximum likelihood, right? Do you remember what we were saying is we have this observation model. Here we have many, many observations, right? So this corresponds to observation 1, to whatever number of observations, right? And then what we were doing is this assumption that these observations were independent, right? And after some manipulations, basically applying the log, minus log of these models, which, by the way, these were explained in lecture 5 for two-dimensional landmarks, but here you can use any kind of function. We derived this result, right, which was very interesting. We got something like this. We had a max of all these probabilities. Well, it was not exactly P, right? It was like, okay, some factors, right? We had, no. Yeah, so this is right. We had this product of all probabilities, right? This is what happens when you have independence assumption, right? And then we did some manipulation, and it turns out that this product, the max of this product is, the result is going to be equal to the product of all inside maxes, right? So inside the max is just looking for each correspondence, and here we had the, right? So that simplified a lot, because with this we saw that actually maximum likelihood with independence assumption and nearest neighbors is the same thing, right? So let me write it this way. Mahalanobis, nearest neighbors. Okay, so that point was some derivation. Today we are going to use something similar, right? So as I said, this is going to be estimation of full trajectories, and for this we are not going to treat them, this estimation as a full Bayesian, from a full Bayesian approach, but actually it's going to be more from, well, maximum likelihood or maximum a posteriori. Okay, so, okay, let me put it this way. And then we talk about another interesting topic, which was the joint compatibility branch and bound, right? If you remember, we were always complaining about all these algorithms, although probabilistically sound, they were greedy, right? You were just associating whatever is closest with whatever you are observing. So a way of accounting for this was this joint compatibility. I'm not going to ask you to derive these things. I'm not going to ask you to implement this, no. But it was like a previous assignment before. So the only important thing about this is that you get this idea of now what we are doing is doing the exploration, the exhaustive exploration of all these combinations, right, of observations and landmarks, and actually it's not necessary to explore all of them, right? Branch and bound. Okay, so if you remember, we were creating hypotheses, like if you remember, well, this tree, actually it was like very convenient to use like a tree, right? Each of these was actually an hypothesis, right? Each of these leaves, because it's including like all these pairs of observations and landmarks. And the interesting idea is that, okay, so after calculating like some value, right, that we know that we can use then this value to take a look at confidence level. In this value, we can set confidence level on chi-square tables, right? So with that, we can filter a lot of hypotheses. But the interesting thing is that childs, they are going to have like this chi-square like at least as bad as their parents, right? So that basically allows us to branch a lot to cut a lot of branches that we don't want to explore, right? So it's not, on the worst case, yes, this algorithm was exponentially. We need to explore everything, but given like, well, some hypotheses that are clearly not good, especially if we evaluate them at the beginning, then there's no need to calculate like to evaluate the full tree. Okay, so take a look at the paper, take a look at the notes, and then, but still the idea was to have this general context. Another thing that I forgot to mention last day is that when we create all these childs, here we have freedom actually not to do permutations with respect to all possible combinations, but actually the constraint on observing just a single landmark from an observation comes here, right? So if already we have already observed this landmark, right? Then here on the child, you don't include that option. You don't do the full exhaustive combinatorial of all of them, right? So you are actually excluding some of them. So on the way we build the tree, actually there's also information that we're embedding here. And then, well, there was this confidence test, this is the dimensionality, and this is the confidence, right? Did anyone take a look at any chi-square table around? Did you Google it? No? Okay. Try to Google it. I mean, the numerical values. Well, no, this is a table. So what I mean is a chi-square table giving you like values, right, with respect to different confidence level and with respect to different dimensions, right? So this is a known table, but you should take a look. An interesting thing is what happens with D increasing, right? So you had a question? Oh, okay, awesome, awesome. Well, then that's great. Some of you have already used this, but, well. Okay, so that was it for the data association class. This topic actually goes very deep, and we will discuss later that there's other things that we can do with data association. One of the most interesting one actually is derived from this new paradigm that we are going to discuss now, that is instead of filtering, instead of calculating at each time step which is the best state estimation or the best landmark, now we will be interested in calculating the full trajectory, right? And we'll see then later what are the advantages of doing this and if computationally this is not that intense as it looks like. Okay, so remember SAM, I wrote on the title, it's smoothing and mapping, right? So we'll describe this approach as a full slam problem, almost. Okay, so each of the terms, right? We have a smoothing. What is this term? Basically, this stands for the full trajectory of the robot, right? Or whatever sensor you have, right? So in terms that we discussed before, it will be x from the time 1 to the current time. Whereas filtering, remember that it's always only interested in last state. Well, on the forms that we have discussed. Okay, and then there's the second part, mapping, right? And basically, so far we have just described maps as a set of landmarks, so we will keep this for now. But this could be any kind of representation, right? This could be point cloud. That's still like a more advanced topic, but basically we want to estimate like what is this representation of the map, right? So far we know about landmarks, so we will keep it for today, but in general you know that mapping could be like any other representation that helps on this estimation of your trajectory of your state. Okay, so nothing much has changed. We are just including here more terms. You will see what is the, well, you can assume that this is going to be more intense in terms of calculations, but we'll see actually that there are some advantages. So this is also an alternative to filtering. Remember that actually the formulation of filtering from the base filter always comes from the Markovian assumption. So if you have like your previous state, and this is totally determining your next state, right? We also have like some observations and some actions, but we only needed the last state. We don't need the full history. Now we are going to have the full history, right? So the Markovian assumption, we'll see how this is slightly changed, but this has like impact. And well, I think I basically have this. So full trajectory. It's going to be beneficial, right? And this is true especially for nonlinear systems. Okay. So in a nutshell, this is what we will be doing today, just describing like an alternative method for filtering. Instead of filtering, now we are going to call this smoothing, right? Because we have a full trajectory, but the idea is the same. Same algorithms that we have described before, we are just going to slightly change them, right? So, okay, let me write like some example, some graphical example. This always helps, remember having like some drawings. And imagine that we want to describe this full slam or this now smoothing and mapping problem as a Bayesian network. This is actually, by the way, what we have done so far with filtering, right? We were always, when we were drawing the graphical model, it was always a Bayesian network. Okay, so this is our initial state, right? And let's say that from here, we see the first landmark. Oops. Okay. So okay, let me also, yeah, I think this is going to be better. Okay, so then I'm going to write here what is the sketch of this system moving, and I'm going to write what is the graphical model, right, as we were discussing before. So we have this initial state, and all we are saying is that here we have this. Now the subindex doesn't correspond to time. I'm just numerating the observations, right? But we'll have something like this. And remember that we can observe Z1. Now, we apply an action, and the robot moves, and still we are able to observe this landmark, right? And there's a second observation to a new landmark, right? We have discussed how to create a new landmark, right? So okay, so in this case, we'll have new state. Remember, this is what we want to estimate. And then we have an action, and we have two new observations, right? In this case, this set comes from the first landmark, and there's going to be a second landmark that actually generates the third observation. Okay, so you get the idea. We can keep going. On the notes, you have like, well, that actually this graph, well, this sketch evolves, and then basically there's like many other observations. But the idea is that it always happens the same way. I'm describing now the full graph. What we said before is that we only needed the previous state, right, x1, and that's it for doing the estimation. Now what we want to estimate is the full the full trajectory, right? So this is going to involve also X2. Okay, so graphical model, right? This is a Bayes network. I'm reminding all of you this because later we are going to use a different graphical model, right? So this is not new. You shouldn't be bored. It's fine. This is just repetition of things that we described before. The new thing is going to come on the next section. Okay, so if we have this, before we were just doing filtering of the last state. Now we can actually write the joint probability of all these variables that we have here on the graph, right? And it will look something like this. So we have this joint probability of all actions, actions, observations, map, landmarks, and state variables. Well, let's say poses. Yeah, better. Okay, so this is it. If we factorize this joint probability with the models that we have described so far, we are going to have something like this. We have a prior, right? And then just following the Bayes network, we are going to have here like a productory of all these, motion models. And then we also have productory of all observations, right? And for this, we have discussed a lot during last lectures exactly what they are, right? So here we have the observation model of landmarks, and well, basically that's it. So we have here this, okay, let me write it this way. This is the odometry or motion or transition model. Right here we have a prior that still this is required, and here what we have is observations. Remember that somehow odometry is a way of observing, right? But the key difference here is that odometry actually changes the state, right? Changes our state, while observations are just like a corroboration of what is our state. So this improves. This is the update step. These observations help us for a better estimation, right, of the states. There's nothing that changes. It's simply that we are observing something that is not directly observable. Yes? Prior. No, this is prior with respect to x0. This is the only prior that we have. That could be a different kind of prior, which I'm not going to discuss today. But at least for what we have written here in this graphical model, right? This is the prior that we need a distribution for this in order this to work. That's a good point. Actually, yes, there's actually a prior of all your states. But that's for another. I think that's a topic for a different day, or maybe just for you to go deeper. This is actually, it's a kind of regularization, right? Okay. So what is the objective? Oops. So we want to maximize this joint probability. Remember that before on the Bayesian approach, what we did is, there's no optimization here. We are just calculating what is the proper conditioning, what is the proper marginalization. If you do that, you still get like an estimator. And then we were discussing that the results for linear system is the same as doing this maximization. Now, for nonlinear, this is going to be different result. We are going to get different result, right? So the Basin approach is going to give us a different result than doing a maximization. Okay, so for doing this, we need a little bit of graph theory. today and next lectures I'm going to explain a little more on this, and then we also need a little bit of linear algebra. Right? This is basically how to solve this efficiently, because we have now a full trajectory. What is the reason for doing that? I mean, maybe this is not solvable. Why are you really changing this paradigm to have the full trajectory? So we'll see that actually we have tools that are very efficient that allows us to calculate this solution, right? But we need a little bit of help from other disciplines. Okay. So this is kind of a reminder, context, if you want, for the problem. Now, what we are going to start is redefining the same problem, but now Sam is going to be described as a factor graph, right? And we'll see what is the difference between a Bayesian network and a factor graph. Have any of you used factor graphs before? You have heard about it? Factor graphs? No, it's a technique. The graph representation is called factor graphs. No? Okay. Okay. Right, so, well, to start this definition, a factor graph is a bipartite graph. You will see in a minute what this means. And, well, this is the previous problem. Now, let's say variables or some nodes of the graph, I'm writing them as big circles. And what are our observations are going to be a different kind of nodes in our graph, right, which are these points, right? So every time that you see a point, this corresponds to observation or an odometry. In this case, this corresponds to the previous set one, right? If you remember, we were observing from this initial state, from x0, we were observing landmark 1, right? Now, we have some odometry. So this is going to be also another factor, right? Okay, and basically we can keep going on. You see that the previous Bayesian network is a little tedious to write, right? So we have all these things because here we distinguish between nodes that we can observe, nodes that we cannot observe, and then when we calculate the inference of this, well, basically we have this full Bayesian approach. We need the probabilities for everything, right? Everything here, like all x, all z's. While now, well, with this other kind of representation, we'll see, we'll see how this changes, but you have 2, 3, and maybe that's it, right? Yeah. And then we have some landmarks. Here we have this one. No. Points on the edges. I'm just writing numbers because this corresponds to the previous observation. So if you recall this problem here, this is more clearly written on the nodes, right? If you take the hand nodes, here what I'm writing is Z1, Z2, Z3, right? So the indexes correspond to that. If you take a look at the nodes here, there's a lot of other observations. It's not that you need them. Actually, we'll see that each of these points in the factor graph correspond to the observations, right? While the other nodes in the graph are the variables to estimate, right? So that's why this is a bipartite graph. There's never an edge between nodes of this class, let's say variables to estimate, and I mean, this never happens, right? There's always, edges are always through these two different kind of nodes, right? So that's why this is called bipartite. Okay, well, this is more interesting property, but you see here things are a little more compact, right? So here we have 1, we have 2, here I think this was 3, this was 4 maybe. You see, it's the same graph, but I'm just writing like few lines here, less things, right? But still the same information. Now, so although Bayesian networks are a natural way to express relations, this is slightly another alternative, right? So Bayesian natural. We've seen this, right? So we have this graphical model explained before, but the advantage of factor graphs is that they have a tighter connection to optimization. Now, in this case, we are not going to be estimating. When we calculate the full inference problem, okay, so what is the probability of all these join, of the trajectory on the landmarks, right? This is the inference problem that we want to solve, or posterior, or belief. So we have defined this in many ways, but when we calculate this, actually, we don't require to have the full distribution for all of them, right? We are going to treat them slightly different, right? So factor graphs are connection to okay. We have questions, comments. To express relations. Yes. Yeah, actually, writing equations, it's fine, but writing all these sentences, it's a little more complicated. So please stop me any time that you see this. Right, so then what are we going to do, right? So as I said, observations and actions now are going to be what we call factors. Right? These new variables are not going to be like, they are going to be a different kind of random, well, it's still a random variable, but what these factors do now is that they express relations between state variables, right? So in this case, we see here a factor, right? Always connecting, for in this case, the observation and the state at x0 and a landmark. So factors are just going to express like what is the distribution between these, right? It's not going to take into account the full distribution. What is the distribution of x0? No. It's going to be simpler than that. So it's just going to modulate distributions between variables. Right, and in this case, variables are poses and landmarks. Okay, so what's the difference between this and the thing that we described before on the Bayesian network? Here, if you see, all these distributions are with respect to many random variables, right? With respect to your action, respect to your observation, and then we are going to have another distribution, right, for the current state, and the same happens for the observations of the state, right? So here we have many random variables. Now we have just simplified this, right? And the only distribution that we are considering are those depending on these factors, right? And they just depend on observations and actions, right? So what does this really mean? That if we write all these parameters here, all these variables, just as theta, then the probability of this theta, it's going to be something like this, right? We are going to have still a product of many factors. This is not this is the difference between before. This is not really distribution, right, in the sense of probabilistically complete, and this is not something like this. It's just going to be like a relation. In this case, factor is just from a single of these variables. This could be a prior. And then we are going to have a product that is relating a couple of nodes, right? In this case, right? So we are going to describe later what these things are, right? But getting back to the graph, it's something like this, right? So in this case, this is an example of this, right? We are going to have here an observation, and this is going to be our, and this is an example of a factor. Well, or if you prefer, let's use this other thing. X0 and M1, right? So this factor, this observation that we have set, it's going to describe like this relation between the two of them. But we are only considering as random variables so far observations and actions, right? So we can also assume that each of these factors, I mean, this is just a theory that we need for factor graphs, right? We need to describe what is exactly these factors. But we can do this. We can assume that this factor for just single nodes is actually the prior distribution that we had before. And then we might have like factors for odometry. Right? And this is going to be proportional to the motion model that we described before. Right? So if we define factors this way, then you agree that we have exactly the same thing that we had before on the Bayesian network. Right? And the same happens for the factors here on the observation. Okay, so we are more familiar with Bayesian networks. We have described like this many, many times, but factor graphs are a little new, right? And I understand that we are just deriving things a little slowly, but you will see in a minute like the big picture. But this is the description that we have always used, right? We are going to have a lot of these observations and other actions. We put this together, and this is the joint distribution of all the things that we have. So far, we have not marginalized. We haven't done any other assumption like Markovian assumption, right? We are just putting here all of them together according to this graph, right? So this is exactly, I mean, we are just writing probabilities according to this structure. And then for factor graphs, it's going to be slightly different. The only thing is that we need to define which are the these modulations, right, of these factors that are a kind of node inside the factor graph, and the variables that is a different kind of node in the factor graph, right? So we have two different kind of nodes, but they are always connected this way, never directly, right? You will never see something like this. It's always. So this, if we propose, this could be any function, by the way. Right? But if we propose these functions to be like a prior distribution over motion model and the observation model, then we'll have the same joint distribution. Okay? Okay. So we are just defining things. We are still not pointing out which are the advantages. Yes, please. Which symbol? This thing? No, this is just proportional. Yes. Or equal to something multiplied like this. Right? Because here, these factors, they don't have to be proper distribution. Right? You can define them as proportional if you want. Yes. This thing. No, you mean what is the difference with respect to the Bayesian network that we have defined before? At this point, if I did things correctly, they should be the same. Right? What I'm showing is that the inference problem of estimating this joint probability, you can formulate it from using a Bayesian, Bayes network, or you can use a factor graph, but you have the same joint distribution, right? If for the notation of factor graphs, we need to define like factors. There's this peculiarity of, factors and nodes, right? And then what are edges? But still, if we do this thing correctly, we have a product of all these factors here. If we just multiply or just assume that these factors are proportional to these distributions, they should be the same thing, right? This is what I want you to convince, that I'm not doing any new consideration, any new assumption. I'm just describing the same joint probability, but with a different graph representation. Okay, this is very important. So. Yes. Yes. Yeah, I see. So your question is, if we are going to get confused on the subindexes, you take a look at this. Usually they are subsequent indexes, right? It's not that all against all are going to be connected, right? And you can still have like connections, but actually the indexes here correspond to landmarks. And these indexes here correspond to states. So if you put here like states and then your landmarks, the indexes of these second kind of factors are always going to have, like, at least on the second part, like indexes that correspond to this. So although it's possible, there's not going to be a confusion. And generally speaking, you don't care. As long as you have an observation with whatever index you have in your state variable, and as long as you have like some distribution that is modeling these two nodes, right? Whatever I-1 is and I and whatever, you don't really care, right? You could be having like factors of the same. It's only important to have like the right model, right? So that means in covariance and then maybe a nonlinear function. Okay. These indexes. Yes. No. This is not for any I and any j. This is any pair of factors that you have in your. So this belongs to, let's say, the combinations of all factors that you have here, right? You see, it's not an all-to-all. If not, this will be a dense graph, right? If it's all combinations of y and j's, you will have a dense. It's only those that correspond to this. So in this case, this factor, which we have named 1, is relating 0 and 1, right? It's not all against all. This is just a subset of all the possible combinations of u. If we had like all connections against all of them, this will be a dense factor, a dense graph, but we don't have this kind of problem. Our problem is always sparse because odometry, it's just relating previous state and last state, and observations usually are in your neighborhood, right? So that's what I didn't write here, like subindexes here. Observed. Okay. So all possible will be that you have a dense graph connecting all your nodes. What is the? Yeah, that's a fully connected graph. Yeah, but this is not what we want. Yes.
And by all possible, it means that all possible with respect to that network. So you have some indices, you have connections, and we take into account the connections depicted on our operation.
Yes.
This means
This means that each of these correspond to the observations that we have seen, right? Otherwise, you cannot put these subindexes. So here, there's like a mismatch of subindexes, but you will see. So this is not the same eyes as I was using before, right? This is a little abuse of notation. If you want, okay, let's write another thing. But the important thing is that this is not all of them, all combinations of nodes, all x with all landmarks and between them, right? This is just all those that you have observed, only those. Okay, so here in the base network, we also have the same thing. Here, this is not fully connected. This is just the previous state with the next state, right? So you see that this is kind of a chain. And then here depends on the observations, right? Depends on which landmark you have observed. Okay, so now the question is does everybody agree that we, after doing these assumptions, maybe with this little difference on indexes, but the important thing is the form, that we have obtained the same result for the joint distribution from the Bayes network and the factor graph network? Yes? No? Okay, you can do this derivation later if you want. Well, it only happens because we are assuming that these factors are proportional to these motion models. Okay, well, so this is the assumption that we do. You can derive it, believe it, or whatever. But now we will assume that we have obtained the same identical joint distribution, right, if we do this little assumption. So this is the starting point from now. Okay? We are not inventing anything. Basically, what we want to say is, look, we have a very nice tool, which is factor graphs. They represent the same joint distribution, right? But they are going to have some advantages. So this was an effort to say, look, the distribution is the same, but we are going to use a different tool, right? A different graphical model. Here, everyone is on board on this idea, right? Okay, okay. Later, if you want, you can do the derivations, what you have to do to get things to be identical. But this is the important thing. So now that we have got to this conclusion, Bayesian networks were what we were defining at the beginning, but they were a little tedious, try to define what was the observed variable, what is the variable to estimate. Now we have the same joint distribution, but just represented with a different graphical model, right, which is graphical factor graphs. So what we are going to do is start like some derivations, and then we'll see later that there's going to be like some advantages or some, let's say, differences with respect to the Bayesian approach. So let me write now the transition model. Right, basically it's this factor that we have described, right, between consecutive state variable x. Oh. Okay, since time now it's not going to be like, we are just going to go through all the state variables, we no longer differentiate, right? With time, we know that I is going to go from 1 to t, right? But basically, I'm just going to use now the subindex I, and this should be like, this should hold, right, through all the formulation. So I'm just going to do this slight change, and then the same happens for the action, right? So here I'm just using index SI. But other than that, this is lecture 5. Right, so what we have here is that we have this normal distribution. Now I'm going to write this transition function, which depends on the previous state and this action. Okay, and I don't have space for this. Yeah. And then we have a covariance that it's only the covariance of the action. Right, so remember, well, whatever we are observing, if this is, well, basically this is the noise on the transition function. Right, it could be Ri, if it's already on the state space, it could be BMBT, right, in the action space. Well, after problem set 2, I think this should be kind of, I mean, you have played around with what happens with Jacobians, propagating noise in the action space, state space, and so on. Okay, so we have this distribution, right? And let me write it this way, because actually we will not be interested in this normal distribution, but we will be interested in the exponents, right? So here we are going to have this. GI, and note that here the dependence is no longer with respect to the mean, right? I haven't written anything about the mean so far. This is just the exact value. And what is this thing, right? I'm going to explain it like now, but this is the biggest difference with respect to Bayes networks. Here we will not be assuming, although they are, we will not be assuming that this is a distribution. This is just going to be a value, and that's what we are going to be calculating, the max of our joint distribution, right? Not the entire distributions, but only the max. So slight difference, but start thinking about it. We have this. This is previous state, right? So if you remember, the equation was we were propagating this state, but if you equal everything to, I mean, you basically try to make this as small as possible. This is the thing that we should be observing, this thing to be as small as possible. And then what is modulating this distribution, or this kind of residual, it's just the covariance on the noise, right? So this is the only variable that now stays as a random variable. And that's why we were defining factors to be one of the two out of the two kinds of factors inside the factor graphs, those modulating these state variables. So I think with this, it's a little clear what's happening. It's a little clear, yes? This thing? Yes, this is xi minus 1. Yes, yes, correct.
Is this the definition, or what's where did you get this model from?
Well, we obtained this model from lecture 5. The only difference now is that instead of telling or saying that we have random variables that are x actions that have, well, the random variable from actions is not exactly from there. It's from the noise that we add to the action, right? But instead of being all those random variables and then we have a posterior, the only thing we are saying now is that the random variable is here, just in the action. Now we are going to be given this as a determined thing. If you do this, this is still valid, right? So this is a way of building the model. The difference is on the covariance that you get, right? So we are no longer linearizing and then doing a covariance propagation. What we are doing is we just have one random variable here, which is this, inside this function. And this is it, right? So this is standard covariance propagation of just one random variable. Well, your question was if this is the definition of our transition model. I would say that this is the new definition that we are giving, just given the new way of treating variables, right, on factor graphs. So it's slightly different. What changes here is x is no longer a random variable. Let me write an example for this because I think it's going to be very clear. Let me write.
Now in SAM, we constrain ourselves only to models which are normal over the previous state, right?
No, they are normal. No. The distribution is normal with respect to the noise that you see on the action space. We are not saying anything about the distribution of your state, of x. This example, I think it's very clear because, yeah, it's very subtle. But so this is what we are saying now, right? We have this factor. We know what it is. And this is x of I minus 1. This is the previous one. It's a point, right? Just this is not a random variable, but just like a deterministic. And then what we do is we apply like this propagation, this transition model, right? And after doing this, what we have is x of I, right? So if you have this, and remember that and then we were adding some noise, right? So this is the only random variable that we are using. All this is going to be deterministic. There's here some noise. That's why this thing is now like static point. On the other hand, what we were doing on the Bayesian approach, right? We started with a distribution. Our variables were always distributions, right? And remember that a very convenient way of describing distribution was through Gaussians, right? Thanks to Gaussians and some tricks that we learn about conditioning and marginalizing Gaussians, this was extremely efficient to calculate, right? So the Bayesian approach was basically saying this. You have like a prior distribution, right, with a mean and a covariance. And then if you want to propagate this, it's going to be the same process. The only thing is that here you also have a random variable. So you need to propagate, first of all, to get to xy. You need to propagate with respect to, let's say, this noise in the state space or action space or whatever you have defined. And then there's going to be the previous covariance, right? And this covariance is due to the well, we were linearizing, right? So this was this covariance transformation given the Jacobian, right? And take a look that this is not exactly the same as this one, because here we are considering as input of this algorithm, a distribution. Just happens to be Gaussian. You do propagation, uncertainty propagation, through this nonlinear function, and then what you get at the end, you remember this result, right? Jacobians multiplying left and right-hand side of this distribution. Oh, well, this should be I, right? And here, what I'm plotting here, these two things is because one corresponds to the noise that you have in the action, and the other corresponds to the noise that you had in your initial distribution, right? So the two things together. Now it's a little more clear. Okay, super. So now, with this, you might have this question, no, but are we giving up on having like a full estimation of the, you will see that no, but in terms of calculating, of estimating, which is the maximum value of these states, this is going to be a much more convenient way of calculating this. If you want to do this other approach, let's say it's a little more rigid because all the time you need to propagate things, right? You need to take into account what was your previous covariance. Oh, it was like this. Oh, okay. Let's linearize, and this is the trick here, linearization for nonlinear functions. It's very bad, and once you add this new estimate of your covariance, there's no way of undoing this, right? Well, we'll see that maintaining this just not probabilistic distribution of your xy's, but actually just this maximum value of what your this maximum value of your estimation is going to have like these advantages. We are never adding information here in a way that we cannot undo. So, okay, just yes. because all this is going to be based on the principle that instead of calculating this full Bayesian approach, where we have a prior and everything is a distribution, X, M's, right? Everything is a distribution, Gaussian distribution. You will just be calculating max, right? So you will just be calculating the mode of this, right? All this. Exactly. Because for nonlinear functions, for linear functions it's the same, right? I haven't argued on this, but calculating a Bayesian approach and an optimization approach, you get the same result. But for nonlinear transition functions and observation functions, the two things are different, right? So if we could calculate, and this is a big if, like a true conditioning distribution and true marginalize all these functions through the nonlinearity, then what you will get is not exactly Gaussian, but still it has a mode, right? It has a maximum. So this is what we are going to be doing differently. Before we were calculating all these distributions, and it simply matched, right? Maximum was exactly the mean and the mode. Now we are just going to be saying, okay, so where is the max, right? Is it here? Okay, let's try to reduce the error by matching the max. And it turns out that actually this is also a distribution, right? But this is maybe for next lecture. Okay, one last comment, one last drawing, right? So for the little toy example of transition, I hope this is clear. This should be like good reference. Now, what we have actually is a chain, right? So because we are calculating a trajectory, and this is where the term smoothing comes from. Here, this is the optimization of the full trajectory. So in this case, it's going to be something like this. We have here like this initial state, x0. We have these factors that are modulating. In this case, it's just odometry, right? So we'll have something like this. So we'll have like this kind of thing. And then for the next state, what we are going to be doing is the same. So we have a point, a fixed point, which is calculated by our initial guess, whatever it is. It might not be the max. It might not be the mean. It might be any other point, right? And then we have this kind of cone thin growing, right? So this will be the way for us for estimating. We never take into account the full estimation, right, after doing all this chain of covariance propagation. We just take values here of our best estimation. We just here add like these factors modulating transitions or observations later. And at the end, this is going to give us a solution, right, for the state estimation problem. If you do this for EKF, well, basically you can imagine, right, but you have something like this. This grows into something like this. This grows into something like this. If you see an observation here, maybe this gets reduced. But you see that this is a very rigid structure, right? We are always like calculating the full posterior of everything, right? While this on the other hand is just going to be optimizing max.
So we want to optimize our computational efficiency, right? Because the solution is human solution, right? So we still have the same estimate because we control this mode of our function in the both cases, right?
So no, we don't have exactly the same. So you're asking if we have exactly the same solution for the full Bayesian and for the, let's say, max. No, what we have similar is the same joint distribution. But we are going to do different things. So the full Bayesian approach, what would do is calculate this, right? So you do this properly, you start propagating things, assuming linearity, whatever, and then at the end you get a solution. This, on the other hand, we are going to maximize. Right? So we don't get a distribution. Later we'll see that actually there's like a covariance that still we can calculate here. But it's going to be different. It's just going to be an estimate. Like whatever points is telling you which is your best estimate. Now, instead of giving mean and covariance, we are just going to be calculating max, right, which is kind of just the state variables. Yes, please. No. This is, let's say, this is 1 sigma. Yes. Well, this is equal size because all the time you are not taking any prior into account. This is equal size only if the covariance of your actions is the same, right? But here starts with a fixed point, a deterministic point, which is your state estimation. In this case, I don't know, x1. This is your estimation. It's just a point, vector, whatever it is that you have defined. And I'm writing all these covariances the same because this only depends on the transition function and the noise that you are adding there, right? It doesn't depend on the previous distribution of your x. Now your x is fixed. This is very similar, actually, to the particle filter problem. Yeah, well, that's a way of taking a look at that. So your state representation becomes a single particle, which is your best estimate. And then you are just improving this let's say, single instantiation of your state variables to be max, to be best possible, fitting the best possible observations and actions. Well, how to initialize your problem? That's actually a very hard question, right? So in general, in optimization, initial conditions are very critical. We have discussed that before that we always want to be close to the true solution, right? So the closest you are, the better. But then this estimation, this optimization, what it's going to do is improve your estimation just by moving and checking all the. Imagine this is kind of a chain where everything is related, right? Not in the big picture, but small changes in one estimation here might affect later the residual or the cost function that you are adding here on later propagation. So everything is connected. It's a big chain. And then this optimization is just looking for a way to match all observations on a reasonable way. While here, on the other side, what you do is you just do proper propagation of all uncertainties, right, through all your network, right? But the price to pay is that you need to calculate all of them, even if you don't care. Maybe you just care about last one, right? But if you were doing like full slam properly, then you need to calculate all these distributions, all of them. Because you need to match all observations. For an open loop chain, this is not important, but imagine now that you have here a landmark, right? So if you want to match this landmark, you are going to have the same problem. Maybe the observation comes here, right? This is observation 1, this is observation 2. You want to match them, right? So that means that you need to slightly change the best estimate, not just following like actions, but also trying to match observations. And when you have this kind of behavior, this is where you really need to have like good estimation approaches. If it's just this is open loop, nothing to worry about. You just execute things. But then later, the estimation problem is going to be getting the maximum of all these observations. Actions, observations, everything. Everything should give you the best estimate that you can. Okay. Let's also give an example now of the observation model. Right? The same model as we described in lecture 5. So this is going to be a normal distribution. Here we have this nonlinear function. Remember that here what we are this relation is between landmark and state, right? So in this case, and we have a covariance. In this case, it's the same as before, right? So previously we were using Q, right, as the covariance here on the observations, but it could be any covariance. Remember that it's just that, the observation on the covariance. So graphically what this means is that we have here, like for instance, this robot. We see here like an observation. And whatever X we have, this is going to be fixed, right? And the only thing that is changing is this, well, let's say that what we are calculating here is this distribution, right, around the landmark. While if you remember on the previous example for, this is a factor graph, so this is base. What we have in base is already an initial covariance. Then if you observe like a landmark, right, this thing is going to be this thing with Q, and covariance after propagating things, right? If you remember, this was H, HT plus Q, right? So this is the covariance of the observation. Okay, so it's the same thing. Now you consider here the robot just to be static or a deterministic point. Here the full Bayesian approach was, okay, we have a distribution of our state. We also have a distribution of our observation model. The join or the observation model of the, yeah, the observation model should take into account these two random variables, right? So that's why we have here this composition. Here we just take now like covariance on the observation. So that's it. Okay, so why not? I've given some examples, full trajectory, you can think about it, please reach us, but I think this is just the conceptual idea. This little or slightly change of paradigm is going to affect the solution a lot. The joint probability is the same, right, as we derived it at the beginning, but now we are not treating state variables as random variables. We are treating them as just deterministic variables. Yes? No. You will see in a moment. So this is the joint probability, right? This is the same calculated from the base, well, from the Bayesian network and from the factor graphs, right? Now, what I mean that the solution is going to be different is that we are going to do different things for calculating this. So in option 1, we are going to do a maximization. And option 2, which is the one that we have already used before, we just calculated this posterior. Right? So that's what we did before. This is for EKF, bias. Yes. It's the problem definition is going to be slightly changed. Right? I'm going to define it now, but it's going to be slightly changed. Still, let's say that the big picture is still state estimation, but we are going to take into account different considerations. These things for linear systems are the same, right? So equal. But we're more interested in nonlinear problems. Yeah. Which is what we are going to be discussing today, right? So I have already argued what this means, right, in terms of the distribution. So the observation, it's going to be this only distribution. Motion model, it's going to be slightly different, right? Now we are going to see in action how we can calculate like a solution of this. Solving sum. Remember, smoothing and mapping. So here are these theta variables. Remember that were x and map, right? We have said this many times, but this is now more formally, right? The state estimation problem, it's going to be maximization, right, of this probability, right? This is what we can represent with our factor graph. Remember the joint distribution of everything. Now, we already did this last day, but if you don't remember, we can, this is equivalent to the arc minimization if we apply the minus logarithm, right? So we apply the minus logarithm of this probability, and still the solution is going to be the same, right? So I mean, remember that this is an exponential thing, minus something, right? Here we are just doing minus log. Well, if you want, multiply by 2, right? So we are just going to get this. So maximizing this equals minimizing the exponents. Well, the negative of the exponents. Okay, this is a usual trick that happens a lot when people try to connect minimum, least squares with probabilities. You have a question? Yes.
State, action,
yes.
observation, and what else?
This is observation and this is actions. U, capital U.
And then what's that?
Map. This is the map of landmarks.
Okay, and do we know actions?
Well, this is the thing that I'm going to discuss now. What we have is just observations for actions and observations. So if you apply, okay, so this is going a little, if you apply Bayes rule here, you know that this is going to be proportional to this, right? So, no, wait. The other way around. Okay. Yes, but then when we create this joint probability using the factor graph, the only variables that we know that are going to be given is Z and U. But if you apply Bayes rule here, we calculate the joint probability, but the variables that are like observed, those that are modulating this relation between X and M are going to be the Z, the observations, and the actions, right? So yes, from those, we are just going to be observing one of them. Actually, we know that this is not going to be random variables in the sense that our model is going to be a simplification of this, but this will come later, right? If we treat this as a full Bayesian approach, calculating this joint probability like properly, this is the Basin network, right? But we argue that we don't really want to calculate that because we basically need to calculate all covariances for all the distributions, X and M included. The joint distribution, if we were doing these assumptions, is the same, but how we are going to be calculating this is slightly different. Okay, I'm not sure if I answer you correctly, but basically this is from factor graph, right? This is the full distribution that we get from the factor graph, right? Okay, so now we have discussed what this looks like in the after applying factors, right? If we do the minus logarithm of this, we are going to have something that resembles this, right? So we have the minimum of this, and then here all this probability, we know that in fact is the product of many of these factors, right? So if you remember, there was like productory of all these, well, kind of factors. Okay, A and B. whatever indexes. I'm not going to enter now. So if you do the minus logarithm, then what we have is a summatory, right, of this logarithm and the logarithm of this, and we know that actually these are like normal distributions. So if you do this, we are going to have something like this, a summation of all the factors, now depending on the transition function. So this is the first kind of factors we have. Right here, I'm just writing the covariance at index I, but we know that this covariance corresponds to the noise on the motion model, right? Not related to X, not related to the state, but actually corresponding to the, well, these imperfections on the transition model, right? And we also have all those factors that correspond to observations. In this case, we are observing landmarks. This is the index corresponding to this observation, and this is the landmark that we are observing at K observation. Okay, this, what we obtain with this, whatever initial guess we have of the X variables and whatever we are observing, right? This should be small, right? This is also called a residual. This number should be small. This is what we are trying to do. And then we know that the, well, the distribution here modeling this is the model, the observation model, right? Okay, so just calculating logarithm, we get this is where is, well, logarithm multiplied by 2. This is what is on the exponents, right, on all these normal distributions that we have described before, and at the end what we get is a lot of square forms, right? So this step should be clear. It's clear. Thumbs up. If not, I'm going to repeat it. It's not a threat. It's, yeah. You've done this kind of manipulation before, right, in other classes? Yeah? Yes, because no. No, yes. Okay, well. Anyway, this was self-contained. I think with this, we are kind of ready. We're still like, okay, so how we are calculating this, joint probability, but here, just to keep up with the explanation of the class, this is calculated from the factor graph. We have this joint. Distribution, we calculate logarithm. We get now, and this is the interesting part, we get a bunch of summations, which are these square, also called factors, right? These things should be small. The smaller they are, it means that this is better, more accurate, right? Ideally, we said that, so for instance, let me write what is the transition function, right? We draw it this way. And then maybe we were adding some noise, right? So if we want this noise to be small, imagine perfectly matching things would be that this thing equals this thing, right? So that means that the difference of this should be close to 0, right? Because, well, this noise, remember that we define it as a normal distribution, 0 mean, and this covariance. Right? So if we are doing things well, these two things should be the same, regardless of the noise, right? And this is basically what we are trying to do. We have here some noise. Ideally, at 0, things were like match nicely, right? And then what we are going to do with this optimization is we are going to force like going like one to some. We are going to like basically move over this. This is a one-dimensional space, but in general, well, it's going to be higher dimensional. But we are going to force this. So the minimum of this would be at 0, right? This is exactly equal this. But then maybe this affects other factors. And this is the problem that I was describing here when I was plotting this kind of chain of things, right? Not chain, but kind of connected, well, basically this is a graph, right, of things relating observations, relating actions. So if you change one of them, it's going to affect the others. But we are simply looking for what is the best way of adjusting everything such that everyone stays happy. This is the same as saying as the joint probability is maximum. Okay, so, well, again, this simplifies a little things. Yes? It's not individually best. If you take a greedy approach, yes, jointly, this is the optimum that you can find, but assuming that this is your cost function, the joint probability. If you had a different cost function, maximum might be different. This is very important, actually. Different cost functions might give you different optimal points. So it's just because we have defined it, but it's simply very convenient, right, to define our cost function to be the probability. Because this is what we are always looking for. What is the best estimation of, so that should be maximum, maximizing our probability, right? If you happen to have a different cost function, like, I don't know, here you add some risk or something else, then we'll be talking about a different thing. But this is just optimum in the sense that this, with respect to this cost function. Okay, so everybody sees this clear. The optimum case will be this equals exactly this. And then in this case, you have a residual that is 0. Awesome. But what happens with other factors affecting this, for instance, this state variable or this other state variable? Maybe they are not 0. And this is where we need to do the optimization, the joint optimization of all of them. Okay, so because imagine, so at the beginning, this is your initial estimate, you just propagate things, and this is your next estimate. The residual of this is 0. You're exactly matching, you're exactly just doing the transition function of this variable. But this might not be the best thing, jointly speaking. Okay, so, well, here's the picture that I want to show. So now the problem has become this big, long list of factors, and the only problem is that they are nonlinear. So this is nonlinear least squares problem. Okay, but at least this is something that is known in other fields, right? This is a problem that is typically used like in many other disciplines, I believe, and we are also going to be using this. Still, this is very general. So we just come to this description of the least square problem from a probabilistic approach, but now we need to define how to define this. Just as a curiosity, you could derive the same result for a single iteration of the EKF, right? So, and then these two things will be the same. It's true for one iteration. If you do 2 iterations for the EKF, then it's not going to be true for nonlinear systems. But here we are not deriving anything new. If these things were linear, what I'm saying is that this is exactly what we had before. This is Kalman filter, as I have explained in previous lectures. But unfortunately, we have nonlinear functions, and then makes our life a little more complicated, right? So what is the first thing that we always do when we have a, what? We linearize, yeah. So linearize the nonlinear least square problem. Let me go step by step, because we have derived like some of these Jacobians, but now it's going to be slightly different, because what we want is the residual, right? So what is the residual? This thing. In this case, for the transition function, we have this is the nonlinear part, and then we have minus the previous state, right? So remember, we want to match this to be as close as possible. That's basically, you have this previous state, you execute the action, and whatever state estimation you had later after executing this action should be close to 0, right? Ideally, it should be 0, but that never happens when you have other things. Okay, so then let me approximate this by first-order Taylor expansion. Now, the only problem is that we don't have a linearization point, say mean, right? This is not going to be possible for us now. What can we do? I'm writing here 0 because this is our estimate. If you want, previous estimate. Right, so we are going to evaluate things at the only place that we can. This is the only known state that we have so far. This could be a very bad estimate, or if we are close, it could be a good estimate. Action, we have argued that this is given, right? This is actually our observation, well, our action, but, and then comes the linearization, right? So here, I'm just going to write Jacobian this way, because here it depends on these two variables. First, depends on xi, right? And then, it only depends on xi minus 1. But basically, this is to say that it's this Jacobian from e minus 1 to I, right? This is different as just next propagation in the chain, right? So something like this. I minus 1, I, and then here we might have I plus 1, right? So these two Jacobians should be different. Here what I'm writing is these deltas of x, and in this case the only thing that we can linearize is with respect to the state variable xi minus 1. This is basically going to be xi minus 1, the initial estimate, plus or minus some error. No. Yeah, this is it, right? So this is the linearization point, and this is the variable that we are optimizing against. So I'm just writing here deltas. It's right, this sign, or is the other way around? Well, I don't know. Check. So this is true for this nonlinear function. And then what we have is, okay, you know what? I'm going to remove this part, so it's going to be a little more clear. Minus, and here what I'm writing is the this is the fixed initial point, and this is how much we are going to change this point after. This is also an approximation that we are doing from here, right? So what we are saying is that xy equals this initial estimate that we have plus whatever update we do, right? And this update should give us like a better estimate. Okay, or if you can call these deltas like error perturbation. Okay, so I'm just adding like some extra terms just to make this a little more convenient for later, but all I'm doing is Taylor here. And here I'm just redefining xi to be like our previous fixed value plus whatever update we are going to do. Okay, questions, comments? Let me write it this way. There's going to be this part, which is evaluated at 0. And this part, which are going to be residuals, right? Just constant values. And then there's going to be the other part of the variables that we have included here, that these are over variables, right? And notice that now our variables are no longer x0, right? This is our previous estimate. We don't care. We will only care about these updates, this delta x, right? This is how much we are going to change the state estimation that we have so far. So that's why I'm including them as variables, although here we have xi and xi minus 1, right? These are just our previous estimate. We will be optimizing with respect to these deltas. Okay, so if we rewrite this again, we are going to have something like this, right? So this is going to be the Jacobian. Yeah. Yeah. So this is your previous estimate. This is your initial condition. You need, because this is an optimization process, iterative optimization process, you need an initial condition, right? Exactly, so that's why I'm writing here delta of xi minus 1, right? And if you see here, what is the definition of this delta? I mean, if this xi equals xi0 plus delta, basically delta means the difference between the two, right? So this is a minus. This is a minus. This is a minus. Definition of delta, yeah, so it comes from here, right? So it's this. This is what but because this is the only thing that we're interested in. We are going, because of the structure of this problem, we cannot really optimize with respect to xi. We can only optimize with respect to the update, how much we are improving the error, right? And that's why we are creating deltas of x, right? That's why because the linearization point is not going to be at 0, right? And then you are going to have here x. We know that this is going to create a lot of error. We can just say this. We linearize around what we have now, our best estimate, and then the update is going to be a slight change with respect to that, right? But this is an incremental with respect to this linearization point. Is this clear? It's a good point. It's a very good point. Actually, many of the problems come from here. Where to linearize, where we are exactly updating, and this kind of thing. Okay. Okay, so then if I'm grouping here like these residuals into this variable A, and then here all these, which are all the variables, we get something like this. Okay, just as a reminder, what is this Jacobian? Right, so we have this. And well, I think at this point we have defined like many, well, you have used like in problem set 2, in other places like Jacobians extensively. It's not really hard, you just need to go a little on the equations depending on what they are and calculate this thing, or maybe calculate this numerically, or autodiff, I don't know, whatever you want to use, but you have here a Jacobian. This is it. Right? And linearization point, right? This is the important little detail, right? It's with respect to our current estimate. Best thing we can do. This is the only thing we can do. Before, the best thing we can do is mean, but we had like the entire range of values. Here, the only value that we have available is the previous estimate. We don't have anything else. Okay, so sounds familiar, but it's slightly different. Keep a look at this. Yeah. Okay, now next is observations. Observation model. And I'm going to follow the same procedure. We have some x, some landmark. Remember that here we are not really arguing if it's the best correspondence or not. We will assume that this is given, but you know that actually there's an algorithm to provide like descriptions of this, right? So this observation should match, well, this observation model should match actually the observation that we are seeing. And this is a value. This is something that the sensor is giving us. Okay. So we do the same thing. Remember, this kind of difference should be closer to 0 as possible. In the best case, this should match exactly. So that means that because the noise here on this observation function is 0 mean, right? So the best thing that we can see is that this thing goes to 0. But that never happens really. So what we do is we approximate nonlinear function evaluated the same time as the same as before in the previous estimate, and landmark is the same. We evaluate this at the previous estimate. Then we have a Jacobian with respect to the observation k and the state xk, right? And then I'm going to use the same thing because remember that the update here is not going to be like state variables directly, but just the update of state variables. Xik. And then we have here a second Jacobian, right? That it's basically, if this is with respect to xi, this will be with respect to landmark. And here we have the update on landmark, right? And then finally, we have this set here, right? Minus set of k. Okay, so again, let me rewrite things here or group things a little. So I'm going to go now for the variables. Well, no, the variables are clear, right? So we have here this variable, we have here this variable. Let's find now like constant values that are actually going to be this one. This is the evaluation of this nonlinear function. And then we also have this. Right? And this is what we are going to call residuals. Okay, so far, this is the previous. If we were not doing Taylor expansion, this is the previous definition that we had before for residuals, if you remember this thing. The only thing is now there's this little change, right? We are approximating this with a linear function, and that means that these small perturbations, we need to consider Jacobians. But always residuals have been this. This mismatch between what you should be seeing, this is H calculated, and the observation, the thing that you are actually observing. This should always be as close as possible. Okay. Are we good? Okay. So, well, just again, for clarification, what are these Jacobians? Right, so in this case, this is the H function evaluated at the state variable xik, right? And for this, the evaluation point, it's not just going to be this, but also remember that the observation function depends on the landmark, right? So we need to use the best estimate of our landmark that we have now. So this is the linearization point. And the Jacobian now with respect to landmark. So we need this point, but we are not linearizing around this point. But you see why we need it, right? If we don't have here this point, then how are we going to create like an observation function, right? This is your Jacobian, your landmark. You need this position. If not, this function is not possible. Okay. So, and then Jacobian with respect to landmark. In this case, subindex is k for the observation, and this is the superindex for the landmark. And this is evaluated at the same point, right? Okay. Okay, so just a slight modifications of what we have already discussed. but nothing fundamentally different. But thanks to this linearization process, actually what we can write now is that this problem, this nonlinear least square problems, becomes a linear least square problems, or linearized, if you want. And how is it possible? So I'm just gonna, we have calculated all this expansion for transition function, the expansion for the observation function. I'm just gonna rewrite everything here onto the same minimization. Here I'm writing deltas. Deltas is just a stack vector of your delta x, delta m's, all the updates, little updates that we have to do. Okay, so here we have these factors with respect to transition function. Now, I'm going to do a slightly strange thing, but it will make sense in a minute. So what I'm writing, if you remember here, before we just have delta xi, but do you agree that we can multiply by the identity and it's the same, right? Okay, so we do this, and then we have here residuals, right? Remember, this A is the residual. And then this is Mahalanobis distance, right? So this is half of the factors. The other half actually comes from the other observations. So we have Jacobian of K, Ak. What is the logic for proposing this optimization, or what is the, let's say, derivation until we get to this result? So there have been many steps since we started this class. I'm just going to summarize them again so everyone kind of follows. We discussed about Bayes networks and our previous approach to Bayes filters, right? We propose, or we write again, what is the Bayes network for this kind of problem, which is a full, we want to estimate the full trajectory, right? It's full slam. Well, we have defined this as smoothing and mapping, SAM. Then we introduced, okay, let me do it this way. One. Bayes network, right? Then we introduced this alternative tool, which was factor graphs, right? And then what we said is that factor graphs are slightly different, but they represent the same joint distribution as Bayes network, right? And then the peculiarity of these factor graphs is that the distribution was only modulated by actions and by observations, right? So that means that state variables are treated now just as deterministic points, right? So we no longer can do a fully Bayesian derivation, right? So modulates probability. And then the fourth step is, once we have this joint probability from factor graphs, once we know which are the random variables, which are just observations and actions, right? We are ready to do the definition of the problem, which is max, right? We maximize probability, right? And in this case, we are also including these as random variables, but well, you could be doing something like this. You apply Bayes and rule, and then what you have is joint distribution of U, Z, X, and M, right? But basically what we want to maximize is this joint probability of all observations that we have. And now these things are going to be given, right? So once you agree that we have, this is going to be a little, once you agree that we have once we have this joint probability, what we did is we transformed this into a nonlinear least square problems, right? Remember doing minus log. And now what we have is a linear square problems after Taylor. Okay, so this is all the steps that we have done since the beginning of the class. How we get here, this is not by magic, right? We did all these derivations, and all of them are important, right? Because if you miss one step, then you can argue, but why are you doing this maximum thing, right? Why are you doing this? So all these steps are logical. Here, we check that joint probability was the same. Here, we were redefining things with factor graphs, which slightly changed like the distributions, right? Here, we were just doing max, and then, well, from here, false linearization and all this. We still haven't finished. There's still the most exciting part of it. But this is more or less what we have done today, right? So if you agree with all these points, I think we are good. If not, well, you can review them, but you can always take a look later at this. Okay, so then I'm just rewriting all these Jacobians, but this is going to be useful for when we write well, you will see that then later we can write like a more compact representation with a matrix, right? So that's when I'm writing all these Jacobians. It's going to be almost sparse matrix, but all these terms are going to be important. And then here we have these two Jacobians with respect to these delta t's, delta x and m's, and then we had the residual, right? Okay, so this is what we have so far. Linearization of this, and then you agree that this actually is, well, the assumption, this is an assumption, but still, we haven't done anything wrong unless we are very far away from, unless these deltas are very large, right? If they are small, we are still like good, right? The error on Taylor expansion is just quadratic to these deltas. Okay, so now we need to simplify this expression a little more, right? And how to simplify this? And for this, what I mean is the following, right? So what we have here is Mahalanobis distances all the time, right? And this is not really standard for linear square problems. So for linear square problems, it's known that, well, you have linear algebra tools for you to solve your problem, but we have this little inconvenience, right? So the simplification is going to come from this point, right? Let me write the inverse of the covariance as the information matrix, right? If you don't remember, we introduced this lecture, I don't remember. Marcel, do you remember? No. Okay, well, we introduced the information matrix at some point. Maybe someone can help. No, okay. But you know about information matrix. It's just, yes, lecture 3, when we were doing the Gaussian conditioning and marginalization. That's where we introduce information term. We also know that we can just factorize this matrix by the Cholesky decomposition, right? We know that covariance is positive definite, well, semi-positive definite, and symmetric. And the same is for the inverse, right? So it's also positive definite. Well, yes, positive definite, the inverse. So that means that we can apply Cholesky. And then Cholesky is also known as the kind of the square root of matrix, right? So I'm going to use this notation, but this is a little abusive, but you will see. So each of these L's is going to correspond to this, to the square root of the inverse. Do you agree, right? So first we do the inverse, then we have information. Then you do Cholesky. And then I'm just saying that this thing is L, right? And this is L again. And then we need to transpose. So I'm just saying, yes, L equals to this thing. Why is this going to be interesting? Because, well, and actually we can simplify this a little more. And this is a little, so this is the square root. No problem, right? We can write the exponent this way. But this actually what it means is the square root and then we transpose. So this is a very compact way of representing it, but you need to know that what we are doing here is inverting Cholesky or square root and then transposing, right, for this term. Okay, so everything here holds, right? That if we can decompose this with Cholesky, then yes, we can rewrite things this way. Now comes the interesting part. You can actually use this when you are calculating residuals in Mahalanobis distance, right? So if you write this in vectorial form, not with norms, what you have here is something like this, right? This is any vector. You are multiplying this way, and I'm just going to use this definition that we have here, right? So if you have this, let me take this, and let me take this part again. This only happens because we have the Cholesky decomposition, right? We need the transpose, and we need, well, the one that is not transposed. So these two things are the same, and then actually, we can rewrite this initial Mahalanobis distance just as an Euclidean distance, right? Yes? So this is great because now we have all these requirements. Okay, on this long list of things, we will add 7. So we transform Mahalanobis distance into Euclidean distances. And with this, then things are much more clear for solving the linear square problems. Linear square problem, right? So why is this? Because then our optimum delta is going to be this. Okay, here we have delta. It's almost going to be the same as you had before, but there's going to be a slight change, right? So here we have this norm. I'm going to write here this, and this is the inverse or square root transpose of the covariance of the transition function, well, the transition model. Here we have Jacobian, same as before. I minus 1, delta I minus 1, minus. Okay. And what else? We also have the residual, so we need to multiply by the same thing. I'm just writing in different parts, but it's basically this. And then this is just a Euclidean norm, L2 norm, right? Cool, so that's for the transition function, and then for the observation, we have the same deal. Right? This is going to be pre-multiplying all these Jacobians and all these residual. Right? We'll see later when we have a matrix how these things are actually. Okay, we have this second Jacobian. And lastly, residual, right? Okay, so I said we were going to simplify this, but we have more terms. What happened? It simply turns out that, yes, we have simplified this a lot, because then I can write this on the following way, right? Group all these summations here in a big matrix, matrix A, right, of all Jacobians. And then we have like a vector of residuals, right, which is our vector. And this is norm 2. So this is fantastic result because this is known for solving least square problems, right? You can go to a least square problems and say, look, this is my matrix A, this is my matrix B, solve it. And it can solve it. If you go there and say, look, I have this nonlinear function and this covariance, then you need to do slightly different things, right? But I think with this, you can use, well, tools that are available. So this is the derivation. I hope that all these steps were clear. If some of them are not clear, go over them again or ask us. But this is how we get from this initial estimation of the joint probability into a least square problems, right? So how does this matrix A look like, right? You know that the vector B, it's going to be pre-multiplying all these factors by C and by A, right? So vector B, it's kind of direct, but the matrix A, it's not that clear. So I'm going to give you now like an example of a factor graph. x0, x1, x2, x3. For this problem, actually, these deltas, what we are doing, we are not differentiating between x and landmarks M, right? It doesn't matter for us. It's just state variables that we want to estimate. So we have a stack vector of all these variables, and at the end, this is going to be the update. Remember, this is an update. This is not the solution. And then we have here some landmarks like M1, M2. This is the same problem that we had before. And now let me write like factors this way. So this is 1 prime, 2 prime, 3, well, with tilde, not prime. And now I'm going to write like, so this will be the actions, right? And I'm just going to enumerate also the observations here, landmarks representing states. Okay. Very good. So, yeah, I'm going to keep this. So now what I'm going to do is define what are the dimensions of this matrix, right? If we start like from the top, we'll have like this corresponds to x0, x1, x2, x3. And then, as I said, our variables are just stack variables. It doesn't matter if it's x, it doesn't matter if it's m's, right? So we are going to stack here like m variables. Okay, so this is for the columns, right? Each column, it's going to correspond to a state variable. And then what we are going to have here on the rows is observations, right? In this case, we might have like a prior observation or odometry, or observations, right? So, well, I haven't done this, but basically x0, this is our prior, right? x0 minus x0, our initial state, this is going to be delta, right? So that means that, no, this is minus delta. So that means that the Jacobian for x0, it's going to be this. If you want, forget about the prior for now, but let's go for the first odometry factor that we have here, right? It's going to be this. It's relating state 0 and state 1, right? So here we have this Jacobian, and here we have this other Jacobian, right? So this is for observation here. Well, actually, it's 2. This is the observation here. So let's take a look, right? So here I'm writing this Jacobian from 0 to 1 and minus the identity. Okay, so it makes sense. It's this Jacobian minus the identity, right? And if you see like the matricial form here, this is multiplying delta x minus 1, and this is the identity multiplying xy. That's why this is on the diagonal, and this is on the left, on the diagonal. Right? And what else is here? Well, this is the residual. So nothing else should appear in this row, right? Okay, the same happens for second factor. If I'm not writing things, it's because they are 0, right? We have this. This is first action, second action, third action, and that's it, right? We don't have more actions. So it's this. this action, and this action. At the end, what we get is x3. You can check that all this, well, hold on. Kind of, right? Okay, so we have this, then we can say that all these factors here correspond to odometry factors. This will be prior. Well, yeah. And then basically it goes on the matrix. An interesting thing is here, here I'm just writing the Jacobians, but you should know that on the left, we are pre-multiplying by each of these factors, right? So in this case, we'll have something like this. This is of 2 prime. This is the multiplication of 3 prime. Basically, this is the covariance that we are using in this for the factors, right? For the propagation of the states. They are only like related to the noise on the transition function. So we need to pre-multiply. Or maybe you can do like a block diagonal matrix if you want of all these things. That's up to you. But you need to pre-multiply each of the rows, right, with respect to these things. And then let's go for the observations with respect to, well, just the observations. So in this case here, we have h, 0 to 1, and then this is it, right? So what's the meaning of this? Take a look. H is relating state 0, and it's related landmark 1. So it's this observation that I'm talking about. It's relating state 0 and landmark 1, right? Okay, so if you keep doing this, then you can fill this matrix. By the way, this is also called, well, this is going to be an adjacency matrix of our graph, which is another interesting way of getting to the same result. But what I did is linearizing and then obtaining the matrix. But in fact, if you start just describing the adjacency, it will look like this. Problem is that here we have like pre-multiplications, right? And this thing, we need to take into account covariances, and that's what makes this problem a little complicated, or a little more complex, I would say. This is 2, 2, and then we have observation 3, and for observation 3, it's relating x first landmark and state 3. And well, basically it goes on, right? So this is set 3, set 4, and so on. Okay? Any questions so far? Is it too easy? You are already tired after too many time? No? Yes, yes, you are tired. Okay, so we can do 2 things. I think I have 5 minutes of class, or we can do a break and then finish the 5 minutes. So who wants to stay here and finish? 5 minutes? Who wants to do a little break and then come back? No one. Okay, good. Yeah. I mean, depends on how tired you are. But we have been discussing a lot, right? I think, yeah, it's almost 1 hour and a half since last break. Okay, so now it's the last part. We need to solve the linearized linear square problem. Right? I think everyone agrees now that what we are looking for is this. Yes? No. That's only for matrix A. But this vector of residuals is just multiplying each of the residuals that we calculated before, A and C, and you pre-multiply by the right? So you need to do this. Okay, but I mean, this is just a vector that you are pre-multiplying with different square root covariances transposed. Okay, so what can we do? Well, the easiest approach is we just differentiate with respect to delta, and then, well, yes, you will allow me here to have, well, it doesn't really matter. Okay, but yeah, we have here two. So this should be equal to 0, right? So this only happens if this matrix equals multiplied by delta equals b, right? So this is the kind of solution that we are looking for. We either minimize this thing. I mean, if we want to minimize this norm, then we need to solve this equation. Right? So what's the problem? That A might not be squared. Right? So if we have this kind of problem, I mean, if A is a square, we just do this, right? But if it's not a square, what we can do is this thing? Yeah. Right? Yes. Okay, well, there's other ways of deriving this, actually, but yeah. So another way is we know that we want to solve this, right, to calculate the minimum. We pre-multiply both terms with the transpose, AT transpose, and then this is actually a square matrix that we can invert. Right, so this is called the pseudo-inverse. This works well for non-square matrices. Pseudo-inverse. Right? So next lecture, actually, we are going to talk a lot about this. So what you can do, you can go and tell your favorite linear algebra program, just invert this thing for me. This is going to be bad or very expensive. And maybe there are other better ways of solving this. But still, with this, you get a solution, right? And the thing is that the algorithm, it's not exclusively doing this one time, right? So if you remember, EKF was doing this just one time. You calculate the posterior, and that's it. And then you keep filtering. You keep adding things. You do this until you converge, right? So in this case, let's say calculate A, B, and then we have here like some initial conditions. We calculate optimum. Oops. We update. Because remember, delta is not the solution. It's just an update, right? So if this is delta, then what we have is something like this, or your set of parameters. It's just going to be this. This is going to be your new update. I'm just writing here 0, but maybe you write here like another index, right? Like a sequence, right? So this will be the easiest way. We can also argue that, okay, this falls from another kind of optimization, but not today. And then if convergence, then return. Okay. So that's it. This was the long journey for today. Many assumptions, many steps, and at the end what we get is just solving a linear square problem that we solve iteratively. Right? This is equivalent to EKF just for a single iteration and for a linear system. But the difference is that here, this A is not assuming any previous knowledge of before. This is just the linearization point. Before, EKF was including like all those previous estimates that you have into your covariances, right? And if you remember covariances from EKF, like, I don't know, this was something like this of the form. So that means that this has been linearized. You have here a covariance that has terms that have been linearized. If you relinearize again, you are not going to relinearize these covariances in EKF, right? And this is important because the error, whatever error you have made, is going to stay there forever, right? It might be fine, but it might be like very critical, right? Up to the sense that maybe you're optimizing on the wrong direction, or this can create like strange effects. But here, on the other hand, take a look. We are always recalculating A. It's always happening. We are recalculating A. We don't have any previous assumption on the covariance. There's nothing that our linearization point is assuming from before except what is the previous estimate? What is the previous estimate? That's it, right? But there's no other part that we have linearized that gets through this, right? This is just a vector. Whatever it is, it can be relinearized, it can be updated, it can be anything. That's why we do this iteratively, right? But there's not this sense of the linearization error that we accumulate after doing many steps on the filtering. Here, it's always a batch new update, right? And this is one of the advantages of this approach. It's more expensive, yes, because maybe this inversion, draw inversion, would be like absolutely like too expensive. Imagine if this is your full state, but we'll see like ways of solving this very efficiently. All right, see you, and thanks for staying until the end.